Hello everyone. This video I'm going to show you another example of Newton's second law and also about problem. Like I say, for the car turning problem, I say if you want the car make a turn, that means you change direction. You need the centripetal acceleration. Centripetal acceleration. And let me show. Where's the centripetal? Sorry, it's not. The centripetal force, if let's see, if there's a car, if there's a car sitting on, not sitting on the ground, it's moving on the ground. Okay, that's the car. Okay, that's a simplified problem. You want to make a turn, you need a centripetal acceleration, right? So where did the centripetal? What provide the centripetal? Which one? What force provide the centripetal acceleration? What force? So actually, it's your friction. It's the friction. Okay, friction provide centripetal acceleration. Okay, it's your friction. It's your friction between your car and ground of your car ground. Actually, more specifically, your tire and ground. Your tire and ground have friction, and this friction provide a centripetal acceleration. So friction is truly very important. Without friction, you cannot propel to forward direction, and without friction, you cannot make a turn. Okay, right now let's see a more general problem. Okay, what if a car moving on the bank? Oh, bank turn. Okay, if the road is tilted or banked. Okay, let's analyze the problem. Okay, if the car moving on a bent curve. Okay, let's analyze this problem. Okay, okay, and let's also use the Newton's second law to analyze the system. And I will show you. I will show you the bent circle. The theta will contribute to the corner speed. Okay, corner speed. Okay, if theta is higher, okay, that will allow you to have the higher corner speed go through the corner. Okay, let's do. And why is that? Let's do the analysis. Using Newton's second law to do analysis. Okay, let's treat the car as the object. Okay, it's not object as the point. Okay, and the car is making a turn, so it will have a centripetal acceleration. Okay, so and what force? What force do we have? What force? A car on bank turn. What force do we have? It has the weight. Okay, it has weight. Now let's assume the car has a mass m. Okay, has mass m, and it's moving on a surface, so it will has a normal force. Okay, it also has a normal force. Okay, that's definitely a normal force. Yeah, that's the mg. And it also has that, like I say, it has friction. The friction direction, intuitively, I think it's here. It's also friction. Okay. Okay. So friction. Sorry, I should use friction. Okay, friction is small f. Sorry. Sorry. I make a wrong pen. I use the wrong pen. Sorry. You have the weight, you have the normal force, and you also have friction here. Friction, and friction. Normally, friction is proportional to your normal force. Okay, normal force, and should I really write the vector format? Okay, let's just keep it Just write n. Let's write n. Normal force. And coefficient is mu. Okay. Friction of often proportional to the normal force, and coefficient is mu. Okay, so we can right now analyze this problem. Um, so so the vectors. So for this such problem, we set a coordinate. And for this problem, I set a special coordinate. I set this direction is called x, and this direction is called y. And left is positive. Left is positive. Up is positive. Upward is positive, and left is positive. This will make the analyze easier. So, okay, and then we apply the Newton's second law, F equal to ma. Okay, equal to ma. And it's a vector format, so we have three component type component. Oh, for component, we start from the y component. The y component will have the y direction. What we have? We have mg, and we have the component from n. Do F have component for y direction? I think it has. So let's see. If this is theta, basically this is theta, so this should be theta. I think theta. Mm-hmm. The theta is here. It's also theta here. Okay. So in y direction we have the n, and be careful, it's n cosine theta, right? Okay, n cosine theta. Be careful. N cosine theta is positive, and we have minus mg, and the friction. Do we have friction? I think this is also theta. And friction, the friction has y component. I think it's f cosine f sine theta. You also f sine theta. You equal to m, the mass m a y. Okay, the y direction. Because we are making a turn, we only have acceleration, centripetal acceleration in the positive x direction. Why we don't have any components? So it's n cosine theta minus f sine theta equal to 0, and and f equal to mu n. So n cosine theta minus mg minus mu m sine theta equal to 0. So f is here. If you don't know, f is here. F equal to mu m. So that's the y component. So what's the x component? And x component, we have n sine theta. Be careful, n sine theta, right? N sine theta is positive. Okay, n sine theta positive. Okay, and we'll have for mg has x component. No. F has x component. Yeah, we have f cosine theta. From here, you will see the friction also contribute to the centripetal acceleration. Really, this because if the cosine theta also go to its cosine theta is cosine component is also help the contribute the centripetal acceleration. Okay, so friction also contributes centripetal acceleration. Okay, and then we will have I think, do we have other x component? I think no. Okay, and equal to max, and max x centrimagnitude centripetal is the x direction, so it's v square over r. Okay, so what we have now, so we want to know finally this problem I want to address. We will get a velocity is a function of bank angle. So well, that's my final purpose. For to reach this purpose, I think I need to do a little more algebra here. So f equal let's say I if I it's not theta also theta and yes theta, I just make these f equals mu and sine theta f equals to mu and cosine theta equal to m v square. So, and here I will have a factor the n out. He will become sine theta plus mu cosine theta equal to r and v square. And also finally I will have this v square equal to mm, m and sine theta plus mu cosine theta. And I want to just replace n. And we can obtain n from here. It's another equation. What's the n? Here we will have mm, mm-hmm, and uh, cosine theta uh, equal to mg. So I just replace mg. Oh no, now replace normal force by this one. So what do we will have? So we will reach the conclusion soon. MR M so M should put is mg cosine theta minus mu sine theta times sine theta plus mu cosine theta. And we can divide out, so v square equal to r3 times cosine theta minus mu sine theta sine theta plus mu cosine theta. So the turn, okay, we want to make a why we can have a higher corner speed to make into turn. So this is fixed. Alright, so let's find the turn radius, the circular motion, the radius of our circular uniform circular motion is fixed. G is fixed. So our v square is really function of theta. So do theta really help you to have a higher corner speed? Let's put something on. Let's put something. Let's assume the friction coefficient. Let's say what value you want. The friction coefficient. The friction coefficient. Let's say it's yeah. Let's assume mu is 0.8. So if and we discuss the two situations. The one is which character if theta is 0, no bank, the corner no banked, the v square is equal to rg times this is sine theta 0. If theta is 0, so it's 0.8, and this is 1 minus sine 0 is 1. So v square is equal to 0.8 and rg. Okay, that's no bank. And if the turn is banked, let's say bank, how many degree on? Let's say, mm, Let's pay 45 degree. Ah, sorry. Let's say if it's 45 degree, v square equal to rg, and the sine 45 degree is it's 7 okay, plus 0.8 times 0.7. Let's use cosine 45. Let's use 45 degrees. Much easier to do calculation. After all, what's let me check my cheat sheet. After all, surprisingly, the v squared becomes 9. Is this right? Let me see. Bar RG. Yeah, okay. It become if the tilt angle, the bank angle become 45 degree, the v square becomes 9rg. Incredible. So this gives you the v is roughly 0.9 rg, and this is give you v roughly equals to 3 rg square root. So if the corner bank 45 degree, the v 45 degree is about triple when if you don't bank. Yeah, you bank 45, your corner bank 40 degree, your corner speed can reach three times higher than the corner speed without the bank. Okay, that's why the bank help you to have a higher corner speed. Okay, so this is also a very simple example for simple application for Newton's second law. I hope this give you more understanding of Newton's second law and combine with the uniform circular motion and friction, right? And friction. So it's a combination problem. Okay. Okay, so this is pretty much about the video. Okay, I'll see you in the next video. See you next time. See you in our video next time. Thank you. Bye bye.